After finding the optimal mechanisms that satisfy these conditions of BIC and IIR, let us now look at certain examples of these optimal mechanisms. So first, let us dissect the condition that we have found for the optimal mechanisms. We have solved this optimization problem, which is taking the expected sum of the virtual valuations of all the players, subject to the condition that this this allocation function, is non-decreasing in expectation. And under the assumption of this regularity for all the virtual valuations of all the players, we have found that when all the virtual valuations of all the players is negative, then it's better not to sell that object. That is the optimal mechanism. But if there exists at least one individual who has a virtual valuation which is positive, then we'll allocate the object to the person who has the highest virtual valuation. That is the optimal mechanism. Now this is really a very crucial point, and we'll see what is the implication of this virtual valuations and the maximum virtual valuation, because it will also give some impact on how the payments are chosen. So what we can observe here is that even though we wanted to find an allocation that is non-decreasing in expectation, we have actually found an f, the allocation function, which is non-decreasing, which is even stronger than that. And not only that, it is also a deterministic mechanism. So it gives it wholly, the object is completely allocated to the person who has the highest virtual valuation. So pictorially we can represent this. So suppose these are the space of all regular virtual valuations, and this the larger rectangle represents that. Now we are actually looking for the mechanisms which are BIC, IIR and randomized. So there is a smaller class which is DSIC, individually rational, and deterministic mechanisms. So the optimal mechanism in this larger space is actually living within the smaller space. That's something interesting to know. So with the discussions that we have done in the previous module, we can conclude our understanding into the following theorem. So suppose we assume that every agent has a valuation which is regular. Then for every type profile, if the virtual valuations are negative for all the players, then the allocation is 0. So the object is unsold. So this is the unsold scenario. In the otherwise, when the object is sold, it is sold to the individual whose virtual valuation is the highest. And the ties, if they occur, they can be broken arbitrarily. Now we can also use the payment formula to find out the payments, and the payments turns out like this. So for those individuals who are not allocated this object, for them the payment is 0. For the individual who got this object, its payment will be given by this formula. So let us understand what this means. Let us first look at this second expression. So what does this mean? So this is the minimum value of the type of player I from which player I starts winning. And the first expression as before, so this one is nothing but the inverse function of Wi. So the value at which Witi is equal to 0. So that value of Ti, that type is considered as the W inverse I of 0. Now what we can observe, why did we need this max between these two terms, is because even though player I becomes a winner, so player I does not become a winner until its virtual valuation becomes 0. So the object is unallocated if everybody has virtual valuations to be negative. If there exists exactly one individual whose virtual valuation is positive and for everybody else virtual valuation is negative, then the agent, the player I, will get that object at that point where its virtual valuation just starts becoming positive. So that is the threshold point, which is W minus I of 0, and whichever is larger. So when everybody else has a virtual valuation which is negative, then the maximum of these two things will be the first one, and therefore that is the payment. Okay, so with that formula, so we can actually understand this point between this w minus I0 and ki t minus I when we discuss the examples. So if you want to say it in words, ki star t minus I is the minimum value of ti where I begins to become the winner. So let us now discuss an example to illustrate the previous theorem, in particular the payment formula. So suppose there are two players. One player has a type which is between 0 and 12, and player 2 has a type set which is between 0 and 18. Now this we also assume that the players types are drawn uniformly at random and they're independent among each other. So now if we calculate this wi of ti, that's the virtual valuation of player 1. So this is given by t1 minus 1 by g1 t1 by small g g1 of t1, which is nothing but t1 minus 1 minus, so this is the so the meaning of g1 t1 is the probability that the random variable, this type random variable, takes value less than or equal to t1. Because this is uniform between 0 and 12, the density is 1 by 12, and it is smaller than or equal to t1 is essentially equal to, that probability is equal to t1 by 12. So g1 t1 is given by this t1 divided by 12. Density, as we said, is 1 by 12. So simplifying, we get 2t1 minus 12. Similarly, the virtual valuation for player 2 is 2t2 minus 18. Now let us focus on this table which explains what will be the actions under different type profiles and what will be the payments in this optimal allocation, in this optimal mechanism design problem. So when t1 and t2 are 4 and 8 respectively, so if you plug those values in, you will see that the virtual valuations are negative for both these players. So in that case, the action will be to keep it unsold and both the players pay 0. When the payment, when the types are 2 and 12, so in 2 the virtual valuation of player 1 is negative. For player 2 the virtual valuation is positive. Now what is so then it means that the object goes to player 2, but what will be the payment that it makes? So here comes this formula. It is going to be the maximum of w minus I 0 and k1 t minus 1. So what is k1 t minus 1? So if t1, so if you look at t1 and t minus I is already fixed. So at which point this player starts winning this object? Clearly for player 1, so the other player, the virtual valuation is negative, so it is not going to win. So player 2 starts winning the object only when his valuation becomes positive. Virtual valuation becomes positive. The threshold at which the virtual valuation becomes positive is t2 equal to 9, and it is asked to pay exactly that amount. So that is the payment formula. So similarly, when you have 6 and 6, so in that case player 1 has non-negative virtual valuation, which is 0, and the other player has a negative virtual valuation, so it is sold to 1, but it pays the amount which at which it is starting to become positive, so it pays 6. Similarly, when it has both these players have 9 and 9, both the players have non-negative virtual valuation, but player 1 has a higher virtual valuation, so it is sold to 1, and it essentially looks at what value it starts becoming the winner, and that value becomes 6, at which it becomes the winner. So till this point, everywhere w minus I, w inverse I 0 is becoming the payment in all these cases. Now let us look at a much larger valuation, much larger types for both these players. In this case, in the last case, both these players have a positive virtual valuation. Now the question is, so now it turns out that the virtual valuation is larger for player 2. So here it is 12, the virtual valuation for player 2. For 2 it is 12, and for player 1 it is 4, right? So player 2 wins because it has a larger virtual valuation, but at which point it starts becoming the winner? So in order to find that, we'll have to equate this value, so which is the 4, the virtual valuation of the other player, with the virtual valuation of this player 2. So this is the point. If you solve this T2, that is the point at which player 2 starts becoming the winner, and that is where this point kicks in. So ki star t minus I kicks in. This is the minimum value of ti at which it starts becoming the winner. And if you solve this, this is going to be equal to T2 equal to 11, and that is the amount that player 2 should pay. And that is going to make this mechanism the optimal mechanism. By the way, it is good to mention that this uniform distribution satisfies the monotone hazard rate condition, and therefore the virtual valuations are all satisfying the regularity condition. So the optimal mechanism is actually getting satisfied in this case. Now we can look at a rather simpler example, which is of symmetric bidders. What the symmetric bidders mean is that the valuations for all the players are drawn from the same distribution. So the GI is same, equal to G for all the players, and also the type sets are same. So because of this fact, the virtual valuations are also the same function, and it is easy to see that the virtual valuations will be larger from one player to another if and only if the types are larger, because they already satisfy the regularity condition. So this inequality will get satisfied only if Ti is larger than Tj. So the object therefore goes to the highest bidder. The bidder who has the highest virtual valuation is the same as the highest bidder, and it is not sold if the type that it has does not make this virtual valuation to be equal to 0. The payment will again be the maximum of this W inverse of 0 and the maximum of the maximum valuation of all the other players. So in other words, if you look at this payment, it is nothing but a second price auction with a reserve price. So if nobody has a virtual valuation, nobody's type or valuation is above that reserve price, which is W inverse of 0, then the object is never sold. And if it is larger than that, then it is exactly similar to a second price auction with that reserve price. If there exists one individual who is above the reserve price and everybody else is below, then he pays the reserve price and wins that object. Otherwise, it is a common, an usual second price auction where the highest bidder wins and pays the second highest bid. So if the object is sold, then it is an efficient allocation. Let us now compare the efficient outcome and the optimal outcome. So optimal mechanism design tries to allocate the object and charge a payment such that the expected revenue is maximized, while the efficiency has a different goal. It allocates the object to the individual who has the highest valuation. So let's do a very similar exercise. I'm skipping the details, but suppose there are two players, type is between 0 to 10 and 0 to 6 respectively, and it has uniform and independent prior. Therefore the virtual valuation you can compute, this will be of this form. And then if you create a table something similar to the previous, you can see that whenever the type of player 1, so this is the space of the types when player 1 is on the x-axis, the types are on the x-axis, and player 2's types are on the y-axis. So when player 1's type is less than equal to 5 and player 2's type is less than equal to 3, the object is not sold. So this is the region, this red region is where the object is not sold. Above this region, you can see that this line is the boundary where 2 wins on this side and 1 wins on this side. Now what you can see here is that, of course, when you do not sell the object, this is not efficient because you could still allocate. So you are not allocating the object, but an efficient allocation will give it to the person who values it the most. So that is not efficient. The optimal mechanism is not allocating because the expected revenue is going to be negative. That's all. Here, this is the interesting space. So in this region here, if you look at this, so this is the 45-degree line. So here T1 and T2 are equal. So on this side of that line, T1 is larger, and on this side T2 is larger. So you can see in this region, even though the value of T1 is larger, it is actually getting allocated to player 2 because the expected revenue is going to be larger on that case. So that is contrary. So this is not efficient allocation. Efficient allocation would have given this to player 1, but this allocation, the optimal mechanism is giving it to player 2. The expected revenue that will be earned by the mechanism by allocating it to player 2 is higher, and that is why it can actually violate the efficiency and give it to a different agent.